Nerd alert! Nerd alert! Nerd alert!
G'day folks, it's Clinton Miles here with Gunner Energy Services, and today on Pulling Back the Curtain, we're going to be diving deep in how these relief well, intervention well, active ranging tools work. So what I'm going to do is try something a little bit different. Virtually with our green screen on our whiteboard, if you will, I'm going to go through the fundamental equations on how these wireline deployed active ranging tools work. Stick with me, folks. It's a very interesting video today.
I'm a nerd. So am I.
Okay, folks, remember in relief well active ranging, the introduction to the series, I started out by saying, we have a well that we cannot access. So let me just draw that for you guys. We have an event on surface. And I'm just assuming this is a vertical well bore, okay? So here is the well bore. And we say that we're going to drill a relief well, and we want to talk about that specific type of active ranging, okay? So that's a no access active ranging tool. It's going to be from the relief well where that is deployed. I won't draw the well bore, but let me just draw the path, okay? So this is a tool that is comprised of three parts. We have the electrode that I'm going to draw here, an insulative bridle, and then a probe, okay? And remember, from the previous video, we're going to inject current into the formation right here. We have this insulating bridle and the probe on bottom that's going to detect the resulting magnetic field. This is all deployed via 7-conductor wire line, and I showed the power supply and the grounding point. Okay, so what does it look like? Well, current's going to inject into the formation, and it's going to flow up and down this pipe. So we have some element of current I flowing up and down the pipe, and there's going to be a resulting magnetic field as per Ampere's law. So Ampere's law just states if we have a wire and we have current I that flows on the wire, if we use the right-hand rule and point our thumb in the direction of current flow, we will have these magnetic field lines wrapped about the wire as so, and their sense will be all pointed this way. Okay, so great. In this case, we have these same magnetic field lines that exist. Here they are in three-dimensional space, and you can see that they propagate or travel right through that probe, and they can be sampled. Okay. Now, the first thing we want to do is say, what is our total magnetic field that we see? Let's get some appreciation in this video for what the magnetic field measured is. Okay, so Ampere's law says the magnetic field, B, in units of Tesla, is going to be equal to this constant mu naught times I over 2 times pi times R. Okay, so don't worry about mu naught. It's just a constant. It's the magnetic permeability of space. I, that's the current, this current that's flowing on the target well. Okay, so let's figure out how to define I, or what I is. And what's R? Well, R here, they are referring to the distance. Perhaps they want to call that radius, but that's that distance right here, D. Okay, and let's assume, just for the sake of argument in this case, that let me just do a little erasing here. Let's assume that the distance in this case is 10 meters, or approximately 33 feet. Okay, so let's go ahead and solve for this, see what it looks like. B total, or rather B in Tesla, is equal to 4 pi times 10 to the negative 7. That's the constant, okay? And now we're going to have some value I over 2 times pi times 10 meters away. Okay. Now, I already intimated that we need to understand what this value I is. Well, as it turns out, I is going to be some fraction of the current that you inject at the electrode, okay? Now, you would think that all the current injected, if we injected, let's say coming down the wire line, we had 10 amps, okay? You would think that the majority of the current would flow up the pipe because it looks like the path of least resistance. Well, in actuality, at distance, so that's when we're a considerable distance away, it's going to be some fraction of that. For the sake of this particular video, I'll call it a reasonable assumption is approximately 1%. So if we're 10 meters away, let's say that we're going to get 1% of what we inject actually delivered to the target well. So 1% of 10 amps is going to be 0.1 amps. Okay, easy. Now, As we get closer, there's going to be a greater percent on the target well, and as we get farther away, it's even less still. And you'll see the price to be paid when so little current collects on the target. So let's work through that, shall we? B total is 4 pi times 10 to the negative 7 times 0.1. That's the current that we found through this assumption. 2 pi times 10. So as I was taught by a gentleman and a scholar and the inventor of this original stuff, Dr. Kukis of vector magnetics, now we can just play some quick tricks with math if we've selected our numbers carefully to make it easier on ourselves. So look what we can do. We can say that's 2, okay. This 1 over 10, well that's 2 times 10 to the negative 1 there, we've taken care of that. And we have another 10 to the negative 1, that's that taken care of. And we have 10 to the negative 7, okay. So that's 2 times 10 to the negative 9. Now I love this number. Why do I like 10 to the negative 9 so much? Well, that's nano, isn't it? And any of you familiar with this unit of Tesla, you know that we often measure the Earth's magnetic field in nanotesla. So what's total signal? At 10 meters away, if we're injecting 10 amps down the wire line and we have a 1% delivery onto the target well, it's 2 nanotesla. Not much. Now, let's put that in perspective. Your standard MWD survey, oh, it'll fail if you get, plus or minus 500 nanotesla. So you're talking, a tiny fraction of that. Let's just look, for interest's sake, at the Earth's magnetic field. Here's the Earth's magnetic field up here, striking the Earth. And that's going to be, let's say, 50,000 nanotesla at any particular point in America, somewhere around there. Okay, so you're looking for signal, 2 nanotesla into 50,000. So the order of magnitude of things is something like 1 part in 25,000. Okay, so it's a very small signal. And that's kind of the first lesson, or the first thing that I want to impart about the physics of the measurement. We're dealing with a very small signal here, but I'll show you how we make these meaningful determinations of distance and direction, despite the fact that you have such little signal to deal with. Isn't it amazing, folks? I absolutely love it. And please stick with me. We're going to have additional videos. I'm going to break down each one of these equations, show you how these pieces work, so you have a complete, thorough understanding. I'll leave you with this. People ask, okay, well, what is the range of your open hole, access independent bread and butter technique, if you will, of wireline ranging tool, okay, your relief well ranging tool? Well, we can estimate that range, and we have certain practical limits, and you can plug these numbers into the equation yourself, but you can see that we're just not delivering a lot of current to that pipe downhole. And depending on the formation resistivity, the size and weight of the pipe, the mud type used, it may be more or maybe less current delivered. So, of course, the geometry is also a big deal here as well. So, folks, I'll go through how all these different environmental factors come into play here, and it will all appeal to the first principles, the physics of the measurement. I want you to understand why it is we design the wells in the way that we do. It's to augment the performance of the ranging tools, not to put them in their worst possible position. So, folks, thank you very much. I know it's a bit of a long video, but you need to stick with me, because we're going to be doing some just intriguing things and really getting down to the nuts and bolts of how these systems operate. Okay, so that's it, folks. I really appreciate you guys watching. Please follow me on LinkedIn. Do your likes and clicks, as Dan would say. And stay tuned till next time. There's more videos coming your way. Gunner Energy Services. Thanks.